Okay, so this chapter is titled, Will a Precipitate Form? So precipitates are predicted from chemical reactions. So the major species in here, it looks like, are sodium chloride, which is a salt, and lead 2 nitrate, which is another salt. So this is an actual chemical reaction. A classic double replacement reaction where the Na is +1, nitrates -1, so they go together perfectly. Alkali metals are always soluble, and Pb is +2, Cl is -1, so you get this guy, which is the potential precipitate. Look at, they gave you Ksp, which is an equilibrium constant for salts that are not very soluble, but we need to check and see how soluble it is given our information from the problem. So the first thing after you write the reaction is if you're going to mix them, dilution is going to happen. So we're going to do M1V1, M2V2 for both salts. So for the sodium chloride, it's 0.2 times 50 equals X times 550, because 50 mixed with 500 is 550. Okay, and that salt, sodium chloride, comes out to be 0.018 molar for sodium chloride, NaCl, which is 0.018 molar sodium and 0.018 molar chloride. Okay, and then you do it again, but you do it for the lead 2 nitrate, and it's 0.06 molar, and you're using 500 milliliters of it, and your final volume is 550. So do the dilution first, and you get 0.055 molar lead 2 nitrate. Okay, so we're going to set up the equilibrium expression for the salt, the only slightly soluble salt. So how does that always work? That is where we take PbCl2 solid, precipitate, in equilibrium with its ions. Okay, and we do equilibrium because we can tell from this Ksp value that it's not necessarily a super soluble salt. Okay, so what's going to happen now is we're going to set up our ice chart. Okay, this is a solid, so we don't care about it. Now, the lead 2 ions are going to come from the lead 2 nitrate. So for every one of those, okay, we get a lead ion. Okay, now for the chloride, it is 2 times that number. And the question is, well, why? Well, every time lead 2 chloride precipitates out of solution, 2 chlorides come out. Okay, so when you set up your equilibrium expression, I kind of did this backwards. Sorry, I did the ice chart first, equilibrium expression. Remember, it's Ksp equals products over reactants, and then you never include your reactant because it's a solid. Now, here's the thing though. We don't know if we're at equilibrium, so right now we're going to solve for Q. So Q equals 0.055, and then 0.018 times 2, and then remember, raise it to the exponent, and then we don't include lead 2 chloride because it's a solid. All right, so solve for Q. Q in this case equals 7.1 times 10 to the -5th, meaning given these starting circumstances, this is where we are at. Okay, so now we have to compare Q to K, and if you look, both the powers are 10 to the -5th. So really we want to look at this coefficient out here. This is 7.1 and this is 1.6. 7.1 is bigger. So right now Q is greater than K, SP. Okay, what do we remember from that? If Q is bigger than K, it means you have too many products. Okay, a bigger number for products gives you a bigger Q. So too many products, equilibrium will shift to the left to get back to K. So it can drop back down to here. Well, if we're shifting to the left, we are producing solid lead 2 chloride. Solid lead 2 chloride is, yes, a precipitate will form. So let's talk about the other scenarios. If Q equals K, SP, if you get Q equal perfectly to K, you are at what's known as saturation. You're perfectly saturated. Okay? If Q is less than KSP, it means that you have too many reactants. Well, reactants, if that was the case, which it's not in this case, would be this guy, right? Too much of this, and in order to get back to equilibrium, it would want to ionize. Well, if it's moving this way and ionizing, these guys are aqueous. They are soluble. So that would be no precipitate if that was the scenario. So again, to predict whether a precipitate will form, you need to look at your reactants that are forming the precipitate, look at their molarities, and plug in and solve for Q and compare Q to the known KSP value.